In this video, you'll be shown how the relationship between bending moment and curvature can be constructed for elements strained beyond the elastic limit. To begin, we consider a rectangular cross-section whose depth to the neutral axis is measured by the coordinate y, where y max is the distance from the neutral axis to the extreme fibre. From elasticity, the yield moment is given by the following expression. My is equal to the yield stress, Fy, times by the second moment of area divided by the distance to the extreme fibre, y max. More generally, this is written as Fy times by z, where z is equal to the second moment of area divided by y max. And this is called the elastic section modulus. For a rectangular section geometry, where we measure the overall depth of the section by d and the width of the section by b, we can say that firstly, the second moment of area is equal to b d cubed over 12, and correspondingly the elastic section modulus is given by b d squared over 6, since y max in this case is equal to d divided by 2. In order to relate the yield strain to the yield curvature, we draw the strain distribution for the cross-section as shown. So the outer fibres of the cross-section are strained to a value epsilon y, and the curvature is simply the slope of this distribution measured by the angle kappa y. Correspondingly then, epsilon y is equal to d over 2 times by kappa y. So kappa y is then equal to 2 times epsilon y divided by d. So what happens then when we increase the bending moments beyond yield? To do this, we need to state the yield stress in terms of the yield penetration, and we use the parameter beta to represent this. Firstly, as is well known, the yield stress is related to the yield strain by the Young's modulus E, and as we've previously shown, this can be related to the curvature Then, drawing a rectangular cross-section, whose half depth is given by d over 2, and whose width is given by b, we first construct the strain distribution with the gradient or curvature kappa, and we put in the limiting elastic strain as indicated by this pair of dotted lines. Here we say that epsilon is equal to epsilon y, and beyond this epsilon is greater than epsilon y. And we say the position of this line with respect to the neutral axis is given by the quantity beta times by d. The corresponding stress distribution then is as we've shown previously, where beyond the yield strain we get yield penetration. And between these 2 points the section remains elastic. At the centroids of these 2 stress areas we can indicate the forces F1 and F2. The parameter beta is defined as being between 0 and 0.5. When beta is 0, the cross-section is fully plastic. When it's at 0.5, the section is fully elastic. Beta can take any value between these 2 values. We next need to determine the moments by evaluating the forces F1 and F2. This is simply done by considering the geometry of the diagram above. F1 is equal to this quantity of area, B, times by d over 2 less beta times d. And this is multiplied by the yield stress Fy. F2 similarly is given by half times b times by beta d, and this is multiplied again by the stress Fy. So in one case we're evaluating a rectangular area, and in another case for F2 we're evaluating a triangular area. The bending moment is then the lever arm of these forces F1 and F2 times by the corresponding force and summed up. So M, for the bending moment, is equal to 2 times, because we're considering both the forces above and below the neutral axis, 2 times F1 that we've already stated, times by its lever arm, which is given by d over 4 plus beta times d over 2. plus F2 times by its lever arm, which is given by 2/3 times by beta times by d. To understand the expression above, let us consider two basic scenarios for beta. Firstly, if beta is equal to 0, so the section is fully plastic, then the force F1 is non-zero and the force F2 is 0. Consequently, the bending moment is equal to 2 times F1 times by d over 4, which when evaluated is equal to Fy times by b d squared over 4. And this is what we call the full plastic moment capacity for a rectangular section, and this is sometimes referred to as M subscript P. The second scenario is if beta is equal to 0.5, so the section is then fully elastic. Consequently, F1 is equal to 0 and F2 is not equal to 0. The bending moment in this case then is given by 2 times F2 times by 2/6 times by d, which is equal to the yield stress times by bd squared over 6. And we sometimes call this the yield moment, or my. If we then substitute in the values of F1 and F2 into our moment expression, we can then write m as being equal to Fy times by bd squared over 6 times by 3/2 minus 2 times beta squared, or the yield moment times by 3/2 minus 2 times beta squared. So analysing this expression, firstly, if beta is equal to 0, so full plasticity, then our moment is equal to 1.5 times my, and our stress distribution is fully plastic with F1 and F2 acting at the centroid. If beta is equal to 0.5, the yield moment then of course m is equal to my, and the corresponding stress distribution with forces F2. The yield curvature is the curvature at which yielding first occurs, and this is where beta is equal to 0.5. Remembering then that Fy can be written as E times by kappa beta times by d. That then implies that the curvature kappa is equal to Fy over the Young's modulus times by beta times by d. And substituting in beta being equal to 0.5, the yield curvature is then given by 2 times Fy times by E times by d. Normalizing our generalized expression for curvature, kappa, by the yield curvature gives kappa over kappa y equal to Fy times by E beta d times by Ed times by 2 Fy, and that equals 0.5 over the yield penetration. From this, it is possible then to plot the full moment curvature relationship on normalized axes. Key values being 1 and 1 for the yield moment and yield curvature. Up to this point, the section is elastic. Then yielding commences, and eventually a full plastic section is reached, whereby m over my is equal to 1.5. And this curved section, m over my, is given by 3 over 2 minus 2 times beta squared. As we've previously shown, when the whole of the cross-section is yielded, assuming no strain hardening, the stress distribution becomes rectangular. Another way then of analysing this cross-section is to consider the components of this section that are in tension and compression. We will assume that the lower half of this section is in compression, and the area of that is given by A subscript C, and the upper portion is in tension, given by A subscript T. Correspondingly, the compression force C is located a distance yc from the neutral axis, and the force that's in tension T is located a distance yt from the neutral axis. As always, the maximum stress in the cross-section is limited to the yield stress, which is given by Fy. In general, the tensile force is evaluated as T being equal to the area integral of Fy with respect to dA. And this is also the same as for C, the compression force. For a constant yield stress, we can then say that the integral of A is equal to the tensile area which is also equal to the compression area. The full plastic moment, which we earlier denoted as being m subscript p, is then given by the tensile force times by the distance from the neutral axis plus the compression force times by the distance from the neutral axis, and this is then given by the evaluation of the integrals t and c, giving us at yt plus ac yc, all times by the yield stress, and this can be called z subscript s times by fy, where z subscript s is given as the plastic section modulus. Generally, the plastic section modulus can be looked up in cross-section tables, or it can be manually evaluated as shown here. For example, for a rectangular cross-section, we then draw the corresponding stress distribution at full yield, and we note the distance of both the tensile and compressive components from what we call the plastic neutral axis is given by d over 4. So the plastic section modulus, z subscript s, is given by 2 times the area of the rectangle, which is d over 2 times by b, times by the lever arm d over 4. And that's equal to b d squared over 4. This is a purely geometric quantity, so to turn this into a force quantity or a moment quantity, we need to multiply by the yield stress. So MP is given by Fy times by BD squared over 4, or ZS times by Fy. At full plastic section capacity, rotations are indefinite and lead to no further increase in moment capacity. As we shown earlier, the stress-strain curve is idealized in the following way. Where beyond the yield stress, it's perfectly horizontal. Correspondingly, the moment curvature relationship can be idealized in a similar way. We can also have rotations as well. But the full plastic moment capacity is perfectly horizontal. Beyond the theoretical yield moment. Due to there being no increase in moment capacity beyond MP, we say that the plastic hinge has developed, and when a sufficient number of them form in a structure to create a mechanism, we say that the structure is in a state of plastic collapse. Plastic hinges are fully plastic cross-sections. The interconnecting segments of the structure are assumed to remain rigid, and all deformations are concentrated at the plastic hinge. For example, for a simply supported beam loaded by a concentrated force in the center, a plastic collapse mechanism occurs when a hinge, or a plastic hinge, forms at the center of the beam. The connecting sections remain rigid, and there is a corresponding central displacement that is always measured directly underneath the load P. The deformations are then measured by the angles theta and at the plastic hinge 2 theta. Similarly, for a beam that is built in, a sufficient number of hinges develop to create a collapse mechanism. In this case, hinges need to be created at both the ends and in the center, because this is a statically indeterminate structure. Again, we have angles at each end. This time we're assuming they're different because the load is off center. And the deformations of the plastic hinge are given by theta plus alpha. The plastic hinges are, of course, located at the supports and in the center. In general, plastic hinges form sequentially. So, for the example above, if we first consider the elastic bending moment distribution, with MA, MB, and MC, and let's just assume that MC is bigger than MB, which is bigger than MA, then the plastic hinges will form in the following sequence. We will see elastic deformations for the structure initially, with the first plastic hinge forming at the support where the moment is the greatest, in this case MC, and the corresponding force displacement relationship being drawn here. The second plastic hinge forms in the center, and the section that connects the second plastic hinge to the first plastic hinge becomes rigid. It loses its elastic deformations, whereas this section still remains elastic. The next hinge to form then adds to the load deflection curve, and it's showing a gradual change in gradient indicating yielding. And then finally, the last plastic hinge forms at the far support. And all intermediate sections are rigid, and we are said to have developed a plastic collapse mechanism.